Convolution neural network is a different type of deep neural network. Let us see what is the difference. Let us see what is the problem that it is trying to solve. These are specifically created for image recognition systems or object recognition or image processing or computer vision. Basically, all these are different names of the same thing. What is it? Taking the images and then analyzing them. Look at this. This is a vision of a self-driving car. Automatically, it is predicting this as building. It is predicting these as trees. It is predicting this as road, 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 road. These are predicted as cars. Okay. This is predicted as a building as well, small cement pole. Uh, this is predicted as sky. Basically, this is how a self-driving car sees. Basically, it takes the input video, divides it into images. Images are feed as input. After feeding the images as input, it is predicting which side is road and then move in the direction of the roads. CNNs are the ones that are used mostly for image processing. The way CNNs are handled or the architecture of the CNN is perfect for image processing. Okay. You can use for such a complex application, or you can use it for as simple as this application. So this guy is from Japan. He has used CNN for cucumber classification. So this is rank M cucumber, rank BL, rank BL. Basically, previously people manually used to classify these cucumbers one by one. Now you just put them on a belt or somewhere, then automatically this classification will be done. Automatic sorting will be done. It can be used as simple as this application, or it can be used for larger applications as well. So this is one of the application that I have found on YouTube. So somebody was using, during peak seasons, they have to segregate up to 500 kg. So based on that, automatically doing it. Still, he is doing it manually. We can even make it on a belt or somewhere. Automatically, it will do the classification for all these image classifications. So he is the guy who did this. He is saying it is working with 70% precision. Okay. So whenever you talk about image classification, face detection, video analysis, anything related to images, the algorithm that is working behind the scenes is convolution neural networks, CNNs. Okay. CNNs are a specific type of deep neural networks. So within deep learning, the image specialization, the algorithm that is specifically used for detection of the images, recognition of the images, object identification, classification for all of them. CNN is the one that is used. CNN stands for convolution neural networks. We will see what is convolution. We already know what is a neural network. We need to understand what is convolution. We already know that image classification, handling images is nothing but handling numerical data only. All of us, we know this, isn't it? If it is a black and white image, grayscale, then it is a value between -1 to +1 or something. Or if it is a color image, then we will take these pixel values, RGB, isn't it? These are the ones that, so even if when I'm saying it is image classification, internally we are working with numerical data only. However, images are slightly different. I mean, we don't see those numbers. If we see those numbers, we cannot really check what is this all about. But if we see the pixel results, then we will be able to make sense out of it. So computers see this, they can still understand it. Humans see this, isn't it? This is human vision. This is computer vision. Okay. That is how computers see an image. Now, there are two major issues. Two major issues if we use ANN for images. We already used ANN for images. Until now, we used ANN only. It worked perfectly. But when you talk about the real image applications like what I have shown you right now, if you take real images, until now we worked with very, very small images, 16 by 16 or 28 by 28, something like that. But if you take really large images, 1 megapixel image, or even if you take like 200 by 200, this type of images also, then ANNs have two major issues. Issue number one is the number of free parameters or the number of weights. These weights are also known as parameters. The weights, free parameters, they are known as the parameters that we need to find out. Okay. The second issue is ANNs kill a particular property of images called spatial dependence. Spatial dependence. Let us see what is this spatial dependence or local correlation. This local correlation, ANN will be actually killing that local correlation and number of free parameters. These are the two issues. Let us see in depth what are the two issues by ANN when we use it for images. So here is the first issue, the count of free parameters or the number of free parameters. Imagine you have an input layer with 784 pixels, which is like 28 by 20 image. If you have a hidden layer with 20 hidden nodes and output layer with 10 nodes, then you will have 785 into 20. I think this math you already have done it, all of us, isn't it? If you have 784 plus 1 bias, 785 into 20, these many weights, 21 into 10, 210 weights, 15,000 weights are there. That is for what? 784 pixels only. What if I take 1 megapixel instead of 784 pixels, I will have 10 lakh pixels, 1 million pixels will be there. What if I take 1 million pixels, 1 megapixel, the number of weights will be nearly around 5 billion parameters will be there. If you take 1 megapixel with simply 5,000 hidden nodes, so 1 megapixel, which means 1 million into 5,000, if you take 5,000 hidden nodes. 1 million into 5,000, 5 billion parameters. Now that is a too high a number, isn't it? 5 billion parameters to update. 5 billion parameters to update or 5 billion parameters to find out. You have to find these many weights. To find these many weights, how many calculations you will do? The calculations will go into trillions or even more than that. Yes or no? So that is the biggest issue. So problem number one with ANN is too many parameters. Too many. Almost. Sometimes they run into millions. Sometimes they run even into billions if you are using as it is. That is issue number one in ANNs. So for practical problems, if you use ANN, nope, it will not work. When I say practical problem, practical image related problems. For smaller problems, yes, you can somehow use it. It will give you the results. But when it comes to images, larger images, 1 megapixel or practical images, ANN will definitely disappoint you. Okay. That is the first issue. The second issue, in fact, that is a serious issue. This can be somehow even answered. If we have a supercomputer, you would say that I don't care about 1 billion parameters, just find me. Still, you can solve this. The second issue is an important issue. Images have something called spatial dependence, local correlation, spatial integrity is there. Images are not like numbers. Let us suppose if you take the pixels here, pixels over here, they depend on its surrounding pixels. If you give me the surrounding pixels, so pixels around the ear, pixels around the nose, pixels around this tongue, pixels around here, pixels around here, they are all locally correlated, isn't it? These are not like some random values. Pixels around this value are somewhat correlated, related to each other, isn't it? Pixels around the eye, they are related to each other. So there is some local correlation in images. Local correlation means what? The pixels have to be like, you cannot simply rearrange it in any manner. You cannot take this image and cut this down and simply put it like this. Let's say you cut this image into smaller pieces, just club all the pieces in one shot. Will you be able to form exactly the same image by randomly forming it? No, there is some local correlation. Based on the pixels here, the other pixels will depend on it. Okay. But what do we do in ANN? We flatten our images. Let us suppose if the image is given to you like 28 by 28. If the image is given to you like 16 by 16, what do we do? The 16 by 16 image, we make it like 1 by 256, isn't it? We keep them all this like this one, this one, this one. We keep it like one line, we flatten it. Don't we flatten it? Even in the previous example, if you take the image of 28 by 28, we flatten it to make it like 1 by 784. We are flattening it, which was still working for smaller images. Now that flattening trick, flattening, all of you getting what do you mean by flattening an image? Making this image, which is a kind of having a spatial dependency, making it look like a single row. Now that flattening operation, if you do it, then you will lose the spatial dependence. Local correlation will be lost. If you lose the local correlation, it is going to be a problem. Okay. We need an alternative to the pixel level calculations. Have you understood the pixels around the eye, pixels around the nose? Images have spatial dependence. Spatial dependence. Local correlation is there in the images. Have you understood that? That means pixels around a particular point, they are related to each other. Pixels have, or the images have spatial dependence. Converting an image into an array, a single array, let's say it is a 16 by 16 image, it has to be like this only. There is a spatial dependence. If you convert it to a 1 by 256 array, then you may lose the spatial dependence. Do you think in this manner, like 16 by 16 spatial dependence is there, do you think spatial dependence is still kept intact in 1 by 256, or it will be lost? Do you think before building the ANN, are we removing the spatial dependency, or are we still carrying it forward? It will be lost. We are not carrying it forward, honestly, in ANN. But still, it was working for smaller images. It's okay, no problem. But for larger images, it is going to really dent. These are the two major issues. What is the first issue that I have told with ANNs? What is the first issue? The first issue is the first issue with ANNs. ANN for images. Let me not say ANNs in general. ANN for images. For images. What is the first issue? Number of free parameters. Number of free parameters. There are too many. This need to be addressed. Second issue is, which is a serious issue. Second issue is a bigger issue. Spatial dependence. Okay. Spatial dependence, or in simple words, local correlation between the pixels. Spatial dependence or the local correlation. This is the one that will be lost. Spatial dependence will be lost, or local correlation will be lost. There has to be a new algorithm that will address both the problems. Yes, there is a new algorithm that has been addressed. So the story so far is, yes, we do admit, we have all respect for ANN algorithm. It is a powerful algorithm. It is a universal function approximator. We understand all that. However, we want to not just solve the problem, we want to solve it in the stipulated time. We want to solve it in the most effective manner. Instead of directly converting it, each pixel, into this kind of array, we want to somehow carry forward that spatial correlation. CNN, convolution neural network, which we are going to discuss, addresses these two problems. How do you think CNN is going to address these two problems? CNN uses local regions property. What do you mean by CNN using local regions property? CNN will take all these subregions. Somehow CNN take the information from the subregions on the image. It will take the info from the subregion. Somehow that subregions, if you take, instead of taking a pixel, if you take these subregions and carry forward, then the local correlation will be kept intact. Somehow, using some trick, using a new method that we are going to discuss, CNN will carry the information related to subregions. By doing so, what are we saying? Pixels around the eye. Earlier we were saying pixels around the nose. Somehow that information will be carried forward. Local correlation, spatial dependence will be given preference. Somehow that info will be kept intact. Whatever was ANN losing by converting into a flattened array, this will not be lost here. Some spatial or local correlation will be kept intact. Instead of taking pixel level, we will take these subregions, and then somehow take the information from the subregions, carry it forward while building the model. How CNN takes the information from the subregions, how it carries this information forward, then how come it reduces the number of parameters, how come it gives better accuracy, is the story that we are going to discuss as part of the CNN overall discussion. It uses a simple trick or a simple technique called filter. We'll introduce something called a filter. By using a filter, we can pick up the local information. We can somehow keep the spatial integrity or local correlation or spatial dependence intact. What is a filter? We are going to discuss now. Let us understand what is this filter all about. I'm going to first explain you the whole concept of filter in first pass. Again, I will come back to this slide. Again, I'll go through this whole explanation. What happens in the first explanation, you may still have some doubts. Hold on to those doubts. Okay. Maybe after a few slides, those doubts will get clarified. Then once again, when I come back in the second pass, in that explanation, you can ask all the questions. Okay. First of all, let me explain you what is this filter concept. Very simple concept. Once you understand the exact intuition, once you can see this, then it will be very easy. Let us see what is this filter. First of all, why filter is created? A filter is created to extract the information from a portion or from a subregion of the image. Okay. Let us suppose this is the image. It has 1, 2, 3, 4, 5, 6, 7 pixels are there. 1, 2, 3, 4, 5, 7, 6, 7 pixels are there. This is the image. And the blue color one that you see here, that is a filter. What do we do? Here, image is of 7 by 7, 7 by 7 size. Filter is 3 by 3. We run the filter in the rows and columns and we create a new image after applying the filter on the existing image. You run the filter in the row wise as well as in the column wise. So you run the filter like this on the image. When you run like this, it will give you a new image. Hey, what do you mean by running the filter? What do you mean by applying the filter on the image? What exactly that means? First of all, image means pixel values only. So look at this. Let us suppose this is the image. And I intentionally took these pixel values just to make sure that the calculation and understanding is easy. Okay. So here are the pixel values. This is the image. And this is the filter, 3 cross 3 filter. And these are the values in the filter. You can have any value in the filter. As of now, I took every value as 111. Okay. Now, when you apply this filter on this image, it will give you a new image. New pixel values will be given and these new pixel values put together will form a new image. You apply this filter on this image. Now this is a subregion. You get all the information from the subregion and then you form a new pixel. And this particular pixel, it is not a single pixel. It carries the information from the subregion of the original image. When you apply this filter, you create a new image by calculating the dot product. What do you mean by dot product? Very simple concept. Corresponding values will be multiplied and added. So 1 into 1 plus 1 into 1 plus 1 into 1 plus 1 into 1 plus like 0 into 1 plus. Since all of these here are ones only, so the multiplication and the dot product will be very easy. Since it is just simply multiplying with ones and then addition, since there are 3 zeros, if you apply this dot product on this one, 6 will be the result. Are you convinced with this? Look at this. What do you mean by dot product? So 9 values will be there. 1 into 1 plus 1 into 1 plus 1 into 1, 3. 1 into 1, 4. 1 into 1, 5 plus 1 into 0. Corresponding values. Like that, how many values are there? 6 values are there. Then you add all of them. 1 into 1 plus 0 into 1 into 0 into 1 into 0. So these 3 will be 0. These 3. 6 is the result. Now you move the filter here. If you have understood this whole process, can you tell me what is the number that I have to fill here? If you have understood how filter is applied on the image and this is how it is obtained, 6 is obtained, what is the number that will come here? Tell me logically what is the number? All of you need to answer this question. So basically you move the filter by stride one. Stride one means you just skip one and then you come over here and then apply the filter, do the dot product. What is the result when you do the dot product? Corresponding elements will be multiplied and the result will be added. The answer is 5. Spot on. If you still want to do one more exercise, tell me what is the number over here. What is the number over here? That means this filter is applied on this particular portion. The next number is 4. Like that, you keep on applying the filter. Now, this is the original image. You applied a filter on it and it forms a new image. This is known as convoluted image. This is not the original image. This is a convoluted image. Now you know how these numbers are obtained. How these numbers are obtained? By applying a filter on the original image. This is a filter. What is a filter? First of all, a filter is nothing but a matrix. A matrix of some values. What is an image? That is also matrix only. You apply one matrix on other matrix, do the dot product of the corresponding elements, add all of them, then you will get a new image. So this is the original image. This is the convoluted image. How do you get the convoluted image? By applying a filter on the original image. Now, this particular filter is also known as kernel matrix. Filters, technical term. Filter is the usual term that is used. Okay. The technical name for this is kernel matrix. Until now, is it clear? Filter means a matrix with some values. We run a filter on the original image. Why do you run a filter on the original image? So that you can somehow, instead of just taking pixel by pixel, each pixel or each value over here is not just result of one pixel. It is result of a particular sub region. All the information, this carries sub region info. This is also known as kernel matrix, and there is no rule that the values of the kernel matrix have to be exactly precisely 1. There is no rule. You can have different type of kernel matrices. You can have another kernel matrix which looks like this: 1 0 0 0 1 0 0 0 1. Yeah, this one. The mic has some issue. Is it better now? Let me just rearrange. Yeah, looks like there is some niggle. So these are just checking once again. Can you hear me clearly without any issue? Yeah, perfect. So the values of this kernel matrix need not be ones always. They can be any value. You know what? If you change the values of this kernel matrix, listen to me carefully. If you change the values of this kernel matrix, a particular feature of this image will be highlighted here. By changing the values of the kernel matrix, you can highlight a particular feature, you can suppress a particular feature of the image. What do you mean by highlighting the features or suppressing the features? If you change the values of this filter or the kernel matrix, there are, like, based on the values, there are some kernel matrix that are there to enhance the intensity. If you apply a different filter, that will make the image smooth. There are some kernel matrices that will make the image sharp. What is the difference? The values that are here, those will be the difference. So here is another kernel matrix. Obviously, you have already understood the fact that if you change the values of the kernel matrix, then the resultant image will change. Yes or no? Because if you keep all of them once, then this number will be 6. If you keep like this number is coming as 3. Can somebody tell me what is the number over here that I'll be filling? If I'm applying this kernel matrix, which is slightly different. Earlier it was all ones. Now it is a slightly different one. If I'm applying this kernel matrix, what is the number over here? Tell me. Apply the dot product. of that kernel matrix or of that filter on this subregion, if you move it, then what is the number over here that I'm going to fill? Carefully you do the math and tell me. Do the dot product. Check that out. It should be 1 plus, it should be 1 1. That's it, isn't it? The answer is 3. I think somewhere here I have written it wrongly. It should be 3, isn't it? Or are we doing anything wrong? Can you check that, all of you? It should be 3, isn't it? If you do the dot product. What we worried about is only this one. Within this, 1, 2, 3. Yeah, it should be 3. I think this 4 is wrong. 3 is correct. So, based on the kernel matrix values, the resultant image will change. In the resultant image, based on the kernel matrix, there are particular features that are highlighted, or particular features that are detected using a particular kernel matrix. There are some kernel matrices that are there to detect the curves. There are some kernel matrices that are there to detect the circles. They will highlight only circles. They will take the image as input, original image. If you apply that kernel matrix, only circles will be there in the result. Nothing else will be there. There are some kernel matrices that are there to detect the sharp edges. There are some kernel matrices that are there to just detect the lines, straight lines. Let's say this is the original image. If you apply this particular kernel matrix, in the resultant one, you will have only straight lines left. Maybe all the vertical lines will be there. If you apply another kernel matrix, only horizontal lines will be there. Everything will be suppressed. Do you believe in that seriously? Shall we see an example where when you apply a particular kernel matrix, what it will give in the result is it will simply give a particular feature will be highlighted. Look at this example. Look at this example. These are the original images. 1, 0, simple ones. Later on, I'll show you somewhat complex ones. 1, 0, 3, 6. These are the original images. If you apply this kernel matrix, if you apply this kernel matrix, what will happen if you apply this kernel matrix on this? Surprisingly, what will happen is this kernel matrix has a property. It will highlight only vertical lines. So in this, are there any vertical lines? Yes, this will be highlighted. In this, what lines will be highlighted? This line will be, this is vertical line. This will be highlighted. This will be highlighted. This will be suppressed. This will be suppressed. Suppress, 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 highlighted. Suppress, suppress, suppressed. Yeah. Yeah, I'll answer the questions in the second pass. First of all, just hold on to all the questions. In the second pass, or maybe in the next slide, your questions will be answered, isn't it? Let me go through that one full round. That will be easy for you. Otherwise, it will be confusing. So some kernel matrices will highlight particular properties. Okay. Look at this kernel matrix. This will highlight only straight lines. When you apply this kernel matrix on this, it is highlighting only straight lines. This is a vertical, specifically it is highlighting vertical lines only. It is highlighting those features. It is detecting, basically this particular kernel matrix is a vertical line detector, feature detector, vertical line feature detector. This is the kernel matrix. If you apply another kernel matrix, now this is 0, 0, 0, 1, 1, 1, 0, 0, 0. If you take 0, 0, 0, 1, 1, 1, 0, 0, 0 this way, this will highlight only horizontal lines. So here vertical lines highlighted, vertical lines highlighted. This will highlight horizontal lines. There are no horizontal lines, nothing highlighted. 2 horizontal lines highlighted, suppress, suppress. 3 horizontal lines highlighted, 3 horizontal lines highlighted. Some kernel matrices will highlight vertical lines, some kernel matrices will highlight or detect horizontal lines, some kernel matrices will detect curves, some kernel matrices will detect circles, some kernel matrices or some filters will detect sharp edges, some filters will detect straight lines. You know what? I don't know which kernel matrix to choose. humanly impossible for somebody to come up with the kernel matrices. Yes, we don't need to provide the kernel matrices manually. Point to be noted. Very important note. Yes, there are some kernel matrices that will determine the curves. There are some kernel matrices that will determine the circles, sharp edges, straight lines. We don't need to provide these kernel matrices manually. If we give the kernel matrix with random values, all that you need to give is you configure the kernel matrix with random weights, random values. W5, W6, W7, W8, W9, random values. You just start there. Algorithm will automatically detect those features. I don't know whether straight lines exist or not. If the images have straight lines, then one of the kernel matrix will end up like a straight line detection filter. We have to give sufficient number of filters or sufficient number of kernel matrices with just simply random values. The major advantage of CNN algorithm is you just start with the random values based on the features that are there in your whole image. Based on the features that are there in your whole image, you give the training data, right? Based on the training data, if there are a lot of straight lines, one of the kernel matrix will end up like a straight line detector, feature detector kernel matrix. One of the kernel matrix will end up like a horizontal line. One of them will be vertical line, sharp edges, curves, lines, and all that. Obviously, all the images in this world are formed by features only. All the images in this world are based out of these features only. Do you agree with this point? All of you think about it. No matter what is the image in this world, they are formed out of these basic geometrical shapes only. Do you agree with that point? Every image has these features. Based on these features, we will detect, we will do the object recognition. Yes or no? Maybe car has different type of features, a cat has different type of features. Maybe if we can somehow detect these features, then it will be easy for us to classify car as car, cat as cat. So the features are detected based on the data. We don't need to give them manually. Underline this point. Do not need to give them manually like the way it is here, like the way you have given here. This is just to see. I have given it. But in reality, we don't give it like this. Yes, there are some vertical lines, algorithm will detect. Yes, there are some horizontal lines, algorithm will detect. One of the kernel metrics will end up like this. One of the kernel metrics will finally end up like this. Features are detected based on the data. We don't need to provide the values of kernel matrix manually. If we give random values in the beginning and give sufficient number of kernel matrices, not just one, give many more kernel matrices. How many ever features are there? Those many ever kernel matrices you have to give. And the kernel matrix, is it always 3? Not required. It can be depending on the input image. It can be 5 by 5. It can be 7 by 7. It can be 3 by 3. It can be usually odd number is preferred. Basically what happens is something is in the middle. Few are this side, few are that side. Just to keep that detection easy. Yes, you can have, if you have larger images in the input, you can have larger ones. Yes, this kernel matrix size can also be increased or decreased, but the suggested values keep it odd value. But do you really need to give these kernel values on your own in the beginning itself? Not required. Those are the weights that will be calculated based on the data. What you need to give, you have to give sufficient number of kernel matrices. You have to configure them. So there are some low level features when you're doing object recognition. There are some low level features that you need to detect. Give sufficient number of kernel matrices, give sufficient number of filters that will detect low level features. Can you tell me what are low level features? If you take any image, you zoom into it. Have you ever done this zooming? If you keep on zooming into it, there will be a maximum point beyond which you cannot zoom in. Then whatever you see there, those are known as low level features. In reality, in any image, if you see any low level features, the straight lines, this horizontal line, vertical line, now this type of structure, this type of structure, these zeros, maybe these curves, maybe these curves, these curves, these are the only low level features. Do you agree with me? There will be very few low level features. Do you agree with that? Very few low level features. Then you give sufficient kernel matrices that will detect mid-level features. Can you tell me what are mid-level features? Mid-level features are formed by combining some low-level features. Yes, I have some horizontal lines, vertical lines. Yes, I have some this one, this one. Mid-level features are formed by using some low-level features. These are the combination of a small pattern. Yes, a very minuscule pattern. You can understand that as you zoom out slightly, then you will start finding a small portion. What are high level features? What are high level features? Then you start seeing some meaningful diagrams, isn't it? Maybe low level, mid level, we will not be able to see meaningful diagrams. But when you come to high level features are the combination of mid level features. When you combine all of them, maybe you will start seeing, maybe then you will start saying cat as a cat, maybe car as a car when you have this high level features. Once you have these high level, low level features detected, straight lines, edges, everything detected, once you have mid level features detected, once you have high level features detected, then you are ready for the classification. Once I have the features of the car, once I have the features of the cat, then the classification will be easy. So the first thing that we do, the first layer in convolution neural network is known as convolution layer. And what happens in the convolution layer is we take the image, we apply a filter, it will give us a convoluted image. In that convoluted image, a particular feature will be updated, a particular feature will be highlighted, a particular feature will be detected. That particular layer is known as convolution layer. I'll come to this once again, convolution layer. So this is the actual image, this is a convoluted image. If you apply a filter, if you take this image, if you apply this particular filter, this is known as smoothing kernel. It will smooth. Depending on the values of the filter, your convoluted image result will change, isn't it? I think all of you in this classroom, some time back, you must have used a kernel matrix in your life already. All of us. I think outside world it is known as filter. Have you ever used filter when you take an image? Instagram or even Android phone or iPhone, when you take image, when you run a matrix on top of it, that image will be changed. Have you ever used it? Like you can create some, you can change the image to black and white image or some, what are the other filters that are very regularly available? It is like vintage filter. Have you ever used it? Vintage filter or black and white filter, sharpening or food or something like that. Yes. Yeah. What is that? You just take the image, you apply a filter on it. You take the image, depending on the values of the filter, the result will change. Yes or no? When you change the filter, the result will change. You might have observed it. Then you try to choose the best looking one. Then you put it as your display pic or something. Yes or no? Sometimes some of the filters will highlight some dark portions. Some of the filters will highlight the edges. Some of the filters will make the image look like black, white and all that. So depending on the filter, there are some filters that will sharpen the image. There are some filters that will blur the image. There are some filters that will do the horizontal motion or detect the edges. Original image, convoluted image. I think we all have used filters. Original image, we might have sometime, if like if you're getting bored or something, you might have some days back, you might have played like this, isn't it? Choosing different ways of representing the same image, how these are created. In fact, the name itself in some of the packages or in some of the softwares, you will see the name itself as filter. It will be given as filter, apply this filter. Or sometimes it may be something else, a mode or different style or something, but mostly it is given as filter only. On Instagram, like this is the original image and these are different styles of the same image. But we are not like, this is like making the same image look cooler, but we are not interested in this. Honestly, we are not interested in this. In object recognition, I don't want to really change the image into different ones, make it look cooler and all that. What I'm interested, I want to apply a filter. If this is the original image, I want to apply the first filter that will highlight only horizontal lines. Look at this, all of you. Highlight only horizontal lines, first filter. I want to apply a filter that will highlight only vertical lines. I want to apply a filter that will highlight only curves. I want to highlight a filter that will highlight only L kind of shapes. Like that. But how can I give it by myself? I can't give it. I let the algorithm choose. I want to give filter number 1, F1, filter number 2, filter number 3, filter number 4, filter number 5, filter number 6. Like that, I will give sufficient filters. I'll give sufficient filters, supply the data. Let us suppose I have 1,000 images of car. Cars have these kind of shapes in it. Okay, 1,000 images of car are there. Different shapes are there in the cars. And I'll give 1,000 images of cats. Cats have different features. Yes or no? Cats have different features. Maybe slightly smoother compared to car. Car may have smart, sharp edges. Cats have different type of features. What I'll do is I'll give sufficient filters. Maybe I'll introduce like 20 filters or 20 kernel matrices. I'm not sure whether this is sufficient or not. Maybe I'm assuming 20 filters I'll apply. Then I will start with random weights, randomly initialized weights. Then I will give all these 1,000 images of cars, 1,000 images of cats. Then one of these 20 filters, one filter will finally transpire to feature detection. This feature will be detected by one filter. This feature will be detected by another one. This will share like that. All the car features, all the cat features will be detected. Once I have all the features, then the classification will be very easy in the last layer. Car versus cat based on these features, it will be done very easily. So the first layer, first hidden layer or first layer, it's not be called as hidden layer. First layer in convolution neural network is convolution layer. How convolution layer is created? By applying filters. What are filters? Filters are nothing but some matrices, kernel matrices. How do you come up with this kernel matrix? Can you create your own kernel matrix? You cannot create your own kernel matrix. You give them random weights. You start with random weights. Automatically these kernel matrices will transpire to a feature detection matrix. Okay, so what happens in the convolution layer? New features are detected by applying the filters. Are you with me? That is the first pass. I will now go back to beginning of this explanation. We will again restart from the filter.